So now let us move on to the last method of designing pre-stressed concrete elements that we will study on this meeting, which is called the load balancing method. So actually, the information that we got from the previous discussion, especially the case of the basic concept method, can also be used to derive the underlying principles uh, behind load balancing method. Although in the case of load balancing method, it is usually used when when analyzing a concrete element which is already in its service load condition, meaning the pre-stressing force acting on it, on the pre-stressing reinforcements, are already uh, the effective pre-stress force after losses. So, which is actually the reduced value of the initial pre-stressing force, which is again diminishes in value because of what we call pre-stress losses. And again, those causes of pre-stress losses will be discussed later on the later chapter. And again, additional to that, we know that if the concrete element is already in the service load condition, the bending moment being experienced by that particular concrete element is already due to the moment, due to the dead load or the self weight itself, due to the superimposed dead load, and due to the live load that is being carried by the concrete element at service load. So these moments or these loads are again actually called the service loads, or the which are actually a gravity. These loads are called service loads, which are actually gravity loads. So just like the C-line method, the load balancing method is usually used to analyze a concrete element which is already in its service load condition. But then again, just like in the case of C-line, in my experience, I believe it can also be used on the other stages of pre-stressing, even in initial pre-stressing at transfer, or at initial pre-stressing at transfer with self-weight. So in my experience, the formula that we will derive here later on will can be also be used to analyze a concrete element at other stages of pre-stressing. But most of the time, load balancing method is just used to analyze a concrete element which is already in service load condition. So now to illustrate the concept behind load balancing method, let us consider this concrete beam here that is already subjected to the total service loads that are intended to be carried by the concrete element itself, which are the dead loads, the self-weight itself, the superimposed dead loads, and the live loads. And we know for a fact that those loads imposed to this concrete element will actually produce bending moments all throughout the length of the concrete beam, especially in the case of simply supported beam. And actually, the magnitude of those bending moments that will be produced by these imposed loads, the dead load, live load, and the superimposed dead load, the magnitude of those moments will actually vary from the one end of the simply supported beam to the other end of the simply supported beam, with the maximum value occurring at midspan. So we already know that for the case of simply supported beam, which supports a uniformly distributed load, we know for a fact that the variation of the moment or the moments being induced or produced inside the concrete element of the simply supported beam varies from 0 to 1 support to a maximum value at midspan, and then will again go down to a value of 0 at the other end. So if we will try to graph all of those magnitude, all of those magnitudes, all of those variations of magnitudes from one end to another, the diagram will actually look like this, with a maximum magnitude of moment occurring at midspan, which is actually the bending moment induced by the applied loads. So this bending moment you see here is the maximum moment acting on the concrete element, which is actually the moment due to the combined effect of the dead load, superimposed dead load, and live load. So that is the variation of the bending moment that occurs inside a concrete element as it supports the total service loads, the dead load, live load, and the superimposed dead load. So now, in the case of load balancing method, just to start the formulation of the formulas underlying the load balancing method, actually, for the case of load balancing method, we have a goal. And actually, we have two goals here. And the first goal is actually this. So goal number one in load balancing method, we have to find a load W sub B, which is the balanced load that we are talking about here, that will just balance the moment due to the pre-stress eccentricity. Because we know for a fact that the pre-stressing force acting on the pre-stressing reinforcement at an eccentricity from the neutral axis or from the centroid of the cross-section will actually produce what we call eccentric moment with respect to the centroid or neutral axis, which has actually a magnitude of P times E if we are talking about at midspan. And actually, that magnitude of eccentric moment being produced by the pre-stressing force, say for example at midspan, must be balanced by by the moment that will be induced at midspan by this balanced load that we want to find on our first goal. So we have to find a load W sub B that will produce bending moments, especially as at midspan, which will just balance the eccentric moment that will be produced by the pre-stressing force. And we know that the magnitude of that moment or eccentric moment produced by the pre-stress force at an eccentricity from the neutral axis or from the centroid will have a magnitude of P times E. So the pre-stressing force times the eccentricity. And that eccentric moment, say for example, acting at midspan of the simply supported beam, must be uh, must be balanced by the bending moment that will be produced by this what we call balance load, which is usually this balance load here is actually a this balance load here is usually just a portion of the total service loads, which are again the sum of the dead load, live load, and the superimposed dead load. So you can expect that the magnitude of this balance load here is just is you can expect that the magnitude of this balanced load here is lesser than the sum of the total service loads, which are again the dead load, live load, and the superimposed dead load. So that is our first goal. We have to find this balanced load W that will just produce a bending moment at midspan, say for example, which will have a magnitude equal to, say for example, let's just call the bending moment that will be produced by the balanced load at midspan equal to M sub B, the balance moment. So that balance moment produced by this balance load acting at midspan of a simply supported beam loaded by a uniformly distributed load must just balance the eccentric moment coming from the pre-stress force acting at the pre-stressing reinforcement at midspan. So that is our first goal here on the load balancing method. We must find this balance load that will just produce a bending moment at midspan, say for example at midspan, that will just balance the eccentric moment coming from the pre-stressing force. So now, so again, guys, take note that the, again, may I just repeat, the balance load here, since we are in service load condition already, we know for a fact that our concrete element already supports the total service loads, which are the dead load, live load, and the superimposed dead loads. And again, the sum of those dead load, live load, and superimposed dead loads will be will all obviously be greater than this balanced load here that we will try to find on our first goal. Or saying in other words, this balanced load here will obviously have a lesser magnitude than the total service loads because like what I have said before, this is just usually a portion of the total service loads. So we will just find a portion of the total service load that will produce a bending moment, a balanced bending moment that will just balance the eccentric moment that is being produced by the pre-stress force acting, say for example, at the midspan. So that is our first goal. And actually, that balance moment that is being induced by this balance load will again produce what we call flexural stresses because we know that on this condition the pre-stressing force acting on the pre-stressing reinforcement produces what we call axial stresses combined with the flexural stresses due to the eccentricity of the pre-stress force. So additional to that, since we now added a balance load here, balance load W that produce a balance moment at midspan, that balance moment acting at midspan will again induce additional stress on the concrete section at midspan, additional to these stresses induced by the pre-stressing force, which will look like this. If we will try to graph the flexural stresses that will be induced by this balance moment at midspan, it will look something like this with an extreme fiber magnitude equal to MC over I. So we will just change the magnitude of M with uh, MB. We will just replace the magnitude of M with the balance moment because it is the one who produces this flexural stresses you see here. And again, let us just put a negative sign because we all know that the bending moment acting on midspan produces a uh, counterclockwise moment here at this section. So if that is a counterclockwise moment, the resultant couple of the several forces must be equal to that clockwise moment with the same direction. So with that, to be consistent on the direction of the bending moment produced by the balance load, the flexural stresses on the upper portion of the neutral axis must point towards the concrete element, which will induce what we call compressive force or for stresses. And again, our sign convention for compressive stresses, we usually use negative sign to indicate compressive stresses, while positive for tensile stresses. So in the same manner, if you want to find the extreme fiber stress or tensile stress acting here, induced by the balance moment that is produced by the balance load, it will have a magnitude similar to this MC over I. So again, we just change or replace M by the balance moment because again, it is the one who produces these flexural stresses. And you just have to take note that RC here must be with reference to the bottom fiber. So RC here must be the distance from the neutral axis to the bottom fiber. RC here must be the distance from the neutral axis to the extreme top fiber. So again, we put a positive sign because the stresses, flexural stresses acting below the neutral axis points away or point away from the concrete element. So they are what we call tensile stresses because they point away from the concrete element itself. So these are now the total, these are now the stresses acting on the concrete element at midspan when it is loaded by the pre-stressing force and the balance load that we have found from our first goal. So if we will try to find the total stress acting at midspan due to the pre-stressing force and the balance load, so we just have to add these stresses you see here, the axial stress due to the pre-stressing force, the flexural stress due to the eccentricity of the pre-stressing force, and the flexural stress due to the balance moment. So we will try to add them. The total diagram of the total stress will look something like this. So why is that? So why is the sum why does the sum of these stresses produce a what we call uniform stress acting at midspan? Because we all know that the bending moment here, the MB, just balances the eccentric moment coming from the pre-stress force acting at midspan. So therefore, we can say that PE, the eccentric moment produced by the pre-stressing force at midspan, is just equal to MB. And since they have uh, equal C, equal I, and equal magnitude of moment, but they just have opposite direction here because the stresses induced by the the flexural stresses induced by the eccentricity of the pre-stressing force produces tensile stresses on the upper portion, while the flexural stresses due to the balance moment produces compressive stresses on the upper portion of the neutral axis. So since they just have equal magnitudes but opposite effect or opposite directions, they will just balance each other as well as the stresses below the neutral axis. They will just cancel each other. Since again, PE, the eccentric moment due to the pre-stress force acting at midspan, is just, that eccentric moment is just balanced by the balance moment due to the applied balance load. So since these stresses just have equal magnitudes but opposite direction, they will just cancel out each other. Therefore, the sum of these stresses you see here will just be coming from the axial stress, coming from the application of the pre-stressing force at midspan. So this is now the total stress acting at midspan if we will impose a balanced load on the concrete element. So actually, that is the goal of load balancing method, to produce a constant or uniformly distributed action stress acting at every section of the concrete element itself. That is the goal of applying a balanced load. That's why it's called load balancing. That is the goal for this method, to produce uh, uniform stresses acting at every section of the concrete element. Although, you will see here there might be a problem. There is a problem that will occur in order for us to address that goal of load balancing method, which is to produce uniform stresses at every section of the concrete element itself. And what might be that problem that will occur, that will prevent us from achieving our goal, which is this, to have this kind of stress at every section of the concrete element. So the difficulty that we will encounter on achieving that goal is because due to the fact that the bending moments being produced by the balance load with respect to the simply supported beam varies from zero at the end, or at one end, and then having a variation of moment with a maximum moment at midspan, and then will again vary up to or down to a magnitude of zero to the other end of the simply supported beam. So in other words, the bending moment produced by the applied balance load is not constant all throughout the length of the simply supported beam. While in this case, the eccentric moment produced by the pre-stressing force, if you can notice, the magnitude of the eccentric moment produced by the eccentric force here, or the pre-stress force along the pre-stressing reinforcement, will actually have a constant magnitude all throughout the length of the simply supported beam. So why is that? Why is the eccentric moment due to the pre-stressing force will have a constant magnitude all throughout the length of the beam? simply because the eccentricity of the pre-stressing reinforcement all throughout the length is just constant. So if E is constant, and obviously P is constant, we assume that all throughout our discussion, we assume that the tension force or the pre-stress force acting on the pre-stressing reinforcement is constant all throughout the length of the pre-stressing reinforcement itself. So since E is constant as well as P, therefore you can imagine that the eccentric moment acting here at the end will just be equal to the eccentric moment acting at midspan, and again will just be equal on the eccentric moment acting at any other section or portion of the simply supported beam. So therefore, we can say that uh, the only portion or section on the simply supported beam that will uh, have a balanced condition, meaning the eccentric moment from the pre-stress force is just balanced by the bending moment produced by the applied balance load, that condition will just occur at midspan. Because again, we know that the bending moments varies with respect to the length of the concrete element. The bending moment produced by the balance load varies along the length of the concrete beam, while the eccentric moment coming from the pre-stress force is just constant all throughout the length of the beam. So say, for example, if we will try to find or investigate a particular section acting here. So we at this particular section, we have a eccentric moment due to the pre-stress equal to PE, same magnitude as the eccentric moment coming from the midspan. So the magnitude of eccentric moment here at this particular section is equal to PE. But if you will look on the corresponding magnitude of moment at that same particular section, obviously it will have a uh, magnitude which is obviously lesser than the magnitude at midspan. And since the magnitude of bending moment at midspan just equals PE, therefore we can say that the bending moment here can't balance the eccentric moment coming from the pre-stress force acting at this particular section. So we failed to have a uniform stress acting on this particular section, since the moment acting on that section, which is this, is not equal to this. The flexural stresses that is being induced by the eccentricity of the pre-stress force. So they will not cancel out each other. So the total stress that will act on that particular section will not look like this. It will not be a uniform stress, which is the goal of load balancing method. So that is our main problem here for this particular condition, for having a tendon or pre-stressing reinforcement with constant eccentricity. So now to address that difficulty, we will have our second goal. And what is our second goal? So our second goal here is to have a tendon profile, which is the profile of the pre-stressing reinforcement, which will have an eccentric moment which will balance the moment due to external balance load, so that the resultant stress at every section is a uniform stress only like this. So that is now our goal. We will try to vary the eccentricity of the pre-stressing reinforcement so that the eccentric moment that will be produced at every section will just balance the corresponding bending moment produced by the applied balance load. So that is our second goal for this method, to address to formulate the formulas underlying the load balancing method. We have to find, or we have to vary the eccentricity along the length of the uh, along the length of the concrete element. So now the problem will now be, again, there will be another problem that will occur. The problem now will be, how will we vary the eccentricity? In what way will we vary the eccentricity? Will we make the eccentricity at the end equal to zero? Or will we make the eccentricity at the other end to be above the neutral axis or above the centroid. So in what way will we vary the eccentricity of the pre-stressing reinforcement all throughout the length of the concrete element, so that the corresponding bending moment will just have equal magnitude to the corresponding eccentric moment coming from the eccentricity of the pre-stress force. So actually, we can address that uh, by simply adapting the shape of the bending moment diagram that is produced by the balance load with opposite direction. Obviously, the shape of the tendon profile that we must put here to balance this kind of bending moment diagram must have a similar shape as this, but in opposite direction, meaning if this is concave downward, the tendon profile that we must put here must be concave upward, just like this. So this is how we can achieve our goal, which is to have a uniform stress at every section of the concrete element by applying a balance load. So with that, we can now make sure that the eccentric moment, say for example, at this particular section, will just be equal to the bending moment acting at that same particular section due to the balance load. Since the eccentricity is now different from the eccentricity at midspan. So we can expect that that particular eccentric moment acting at here acting here at this particular section will now be equal to this bending moment acting at this same section due to the balance load. So that is how we can address the difficulty we encountered a while ago. So in that way, we can assure that the total stresses acting at every section will just look like this, because we all know that the total stresses acting at every section is just the sum of the axial stress coming from the pre-stressing force itself and the flexural stresses due to the eccentricity of the pre-stress force plus the flexural stresses induced by the balance load. So in this way, by having this type of tendon profile or profile of the pre-stressing reinforcement, we can make sure that at every section we will have uh, a diagram of stresses look that will just look like this. And with that, we can make sure that this eccentric moment will just be always equal to the corresponding bending moment here, which are actually what we call balance moments. So all of those moments here are now called are actually called balance moments. So they are called balance moments because they are just balancing the eccentric moment produced by the eccentricity of the pre-stressing force all throughout the length of the concrete beam. So there you go. That is how we can address our difficulty we encountered a while ago. So now we can achieve this. We can achieve now a uniform stress acting at every section of the concrete element itself. So now, since we are already assured that all of these bending moments, balance bending moments here, will now just be balanced or counteracted by the by the eccentric moment due to the eccentricity of the pre-stressing force acting at the pre-stressing reinforcement. Now we can now say that the bending moment, the balance bending moment, say for example at midspan, is now equal to the eccentric moment due to the eccentricity of the pre-stressing force acting at midspan. Or in equation form, we can say now that MB, the balance moment at midspan, say for example, is now equal to the eccentric moment due to this pre-stress force acting at the pre-stressing reinforcement, which have a magnitude of P times E. So we are now sure on this relationship. We are now sure that the eccentric moment here at midspan is now equal to the bending moment acting at midspan as well, which is due to the application of the balance load. And we know, on this case, for a case of simply supported beam, which supports a uniformly distributed load, we know that uh, the bending moment, specifically at midspan, is just equal to this formula, WL squared over 8, since we are investigating the midspan section. We know that the magnitude of the bending moment acting at midspan for a simply supported beam, which supports a uniformly distributed load WB, is just equal to WL squared over 8. Therefore, we can change this MB here by WL squared over 8 by also changing W with WB, the balance load. So that bending moment, which is now again equal to WBL squared over 8, is now equal to the uh, product of the pre-stressing force and its eccentricity. Or if we will just express this equation in terms of WB, we can now find the magnitude of that balance load that we have to apply on this concrete element so that the, the eccentric moment due to the eccentricity of the pre-stressing force will just be balanced by the bending moments that will be produced by that balance load. So we can now find the magnitude of that balance load by using this formula here. 8 times the pre-stressing force times its eccentricity at midspan. So since we derived this formula by considering the section at midspan, so the eccentricity that we will talk about here will be at the midspan, divided by L squared, which is the total length of the beam itself, the simply supported beam. Although you have to take note that this is not always the case. This is not always the way to find the magnitude of the balance load that you have to apply on the concrete element itself to just balance the eccentric moment at every section being produced by the eccentricity of the pre-stress force. This is not the only way. Actually, it depends on it depends on the load that will be carried by the concrete element itself. Actually, we can directly say that uh, this formula is dependent on the moment diagram that will be produced by the load that will be applied to this particular concrete element. Say, for example, in this case, if we will apply a concentrated load acting at midspan that points downward, it will have a moment diagram that will look like this, although it is just inverted. So in order for us to counteract all of those bending moments that are being produced by a concentrated load acting at midspan, we must have a tendon profile same as this. So we must have actually what we call a harp tendon profile such as this. Why? Because we know that if the tendon profile is similar to this, if you will try to graph the variation of the bending moment being produced by the eccentricity of the pre-stressing force all throughout the length of the concrete element, the diagram of the graph of that uh, diagram of the eccentric moment being produced all throughout the length of the beam will just look like this, which is exactly the opposite of the moment diagram, which will produce by applying a concentrated load at midspan. So again, if you will have this is how you will decide which tendon profile you have to use in order to have a balance condition on the concrete element. So say for example again, if we have a concentrated load, we know that the moment diagram for a concentrated load, if the beam is simply supported, we know that the moment diagram for a concentrated load applied downward at midspan will look similar to this, but uh, in opposite direction. It must be it must be positive. It must be positive. So in order for us to counteract all of those bending moments all throughout the length of the concrete element here, we must have a tendon profile same as this, so that the eccentric moments that will be produced all throughout the length will look like this, what you are seeing here. So since this is similar to the bending moment being produced by the applied concentrated load at midspan, therefore we can be assured that they will cancel each other at every section of the concrete element itself. So that is how you can choose which tendon profile you have to use to balance the applied load on the concrete element. Or actually, you can look it on a different way. Say for example, if the given is the tendon profile itself. So say for example, we have here a parabolic tendon profile with an eccentricity 0 at the ends. Say for example, if you want to find a a load that will just balance the eccentric moment that is being produced by the eccentricity of the pre-stressing force acting at the pre-stressing reinforcement, we can say that we have to find a load that will produce a bending moment diagram opposite this. Same magnitude of opposite, same magnitude of bending moment, same magnitude of bending moments, but will but must have a opposite direction. So we know that a uniformly distributed load, just like this one, produces a parabolic moment diagram, same as this, which will just counteract or counterbalance the eccentric moments being produced by the stressing force all throughout the length of the beam. So therefore, if you will have a tendon profile as such as this, we have to apply a uniformly distributed load so that the eccentric moments coming from the pre-stress force will just be balanced by the bending moments that will be produced by the applied uniformly distributed loads. So that is how you can find either the tendon profile or the balance load that you have to apply in order for you to have a balanced condition with respect to the moments or flexural stresses acting on the concrete element. So we have different profile here depending on the type of load that you want to balance. So if you want to balance a concentrated moment, say for example, the load that is being carried by the concrete element is a concentrated moment at the ends. So we know that the bending moment diagram that is being produced by that kind of load is similar to this but opposite in direction. So therefore, in order for us to counteract those bending moments all throughout the length of the beam, we must have a tendon profile same as this with a constant eccentricity so that uh, there will be also a constant eccentric moment due to the pre-stressing force all throughout the length of the beam, which will look like this, which will just balance the bending moments that will be produced by the applied concentrated moments at the ends of the concrete element. So that is uh, how you can find this WB. So it doesn't have a formula similar to this always. So again, it depends. It depends on the load that will be carried by the concrete element. If the load that will be carried by the concrete element is a uniformly distributed load, so you can use this formula. But say for example, if the load that will be carried by the concrete element is a concentrated load, you can use other formula. So just derive the formula for finding the, say for example, the bending moment at midspan for a concentrated load. and just equate that to the eccentric moment acting at that same location, which is the midspan, and then just express the equation in terms of the WB or the balance load P that you have to apply here on the midspan of the concrete element. So in that way, you can find the balance load that that must be imposed on the concrete element to have a balance moments at every section, so that you will be sure you will be assured that the stresses acting at every section will be similar to this, will be just a uniformly distributed stress. So uh, again, you have to remember, you have to realize that what we are talking about here is uh, service load condition stage of distressing. So we are in the service load condition here. Everything that we are talking about here now for the load balancing method is in service load condition, wherein the load being carried by the concrete element is the total service loads. And again, just like what I have said before, the balance load here is just a portion of the total service loads. So meaning, uh, there there is still a remaining load that will be carried by this concrete element. So let us just call that remaining load that will be carried by this concrete element equal to W sub UB, uh, the unbalanced load. So again, that unbalanced load is the remaining portion of the total service loads that will be carried by this concrete element, since we are already in service load condition. So you have to remember, we are in service load condition because that is where the load balancing method can be applied, at service load condition. So you can expect that the sum of the balance load here and the unbalanced load here is just equal to the total service loads. So again, just like the balance load, the unbalanced load here will also produce a bending bending moment all throughout the concrete element, all throughout the length of the simple supported beam, which will have a similar shape as this, or in other words, the bending moments at every section will just have additional bending moment coming from the applied unbalanced load. So let us just call the moment that will be produced by the unbalanced load here equal to M sub UB, the unbalanced moment. And because of that, because there is an additional bending moment applied to this concrete element, therefore, there will be additional flexural stresses that will be induced inside the concrete element. Since before the application of the unbalanced load, the total stress acting on the concrete element at every section is equal to this, if you can remember. So if we will try to apply additional load, which is the unbalanced load here, that will produce unbalanced moment. Therefore, there will be additional flexural stresses that will be induced inside the concrete element, which will have a diagram similar to this, with a maximum extreme fiber magnitude equal to this, MC over I. So since the moment that induces this flexural stress is MUB, so that is our M that we have to use on the formula MC over I, as well as on the bottom fiber. So again, you have to take note of the sign, because we know that these flexural stresses acting on the upper portion of the centroid or the neutral axis produces compressive stresses, while on the bottom or the lower portion produces tensile stresses. That's why it has a positive sign. So before the application of the unbalanced load, the total stress acting at every section of the concrete element is just this, a uniform stress only. But since we now applied the remaining portion of the total service loads, which is the unbalanced load here that produce an unbalanced moment here, which produce again additional flexural stresses at every section of the concrete element, with the flexural stress acting at midspan equal to this, which have a extreme fiber stress equal to this and extreme fiber stress equal to this. So now if we will try to find the total stress acting at every section now of the concrete element with the application of the unbalanced force or unbalanced load here, the total diagram of the total stress will now look like this. We will try to add this stresses with an extreme fiber magnitude of stress equal to the sum of the stress here, which is negative P over AC, and the stress acting here on the top fiber, which is equal to this. And similarly, the total stress acting at the bottom fiber is just the sum of the stress here, negative P over C to negative P over AC, and this stress here, which is MUBCT over IC. So those are actually the formulas that you will use to find the total stress acting on a concrete element using the load balancing method. So you just have to take note of these formulas. These are the formulas that you will use if you want to find the total stress acting on a concrete element at every section of a concrete element, which is again in service load condition. So you have to meet that criteria first. The concrete element must be already in service load condition. Since we derive these formulas, considering that our concrete element is already in service load condition, wherein the total loads that it will support is equal to the total service loads, which are due to the dead load or self weight, superimposed dead load, and the live load. So if you will try to get the summation of this again, summation of these flexural stresses here, you can see that the total force acting on this particular concrete section of the concrete element is just a single force C acting at a certain distance from the neutral axis or centroid. So actually that C is just equal to the compressive stress or compressive force we have derived from the C-line method and the basic concept method. So if you will try to investigate this formula, the formulas that we have derived for load balancing method, if you will try to compare that to the formulas we have derived from the basic concept method, you can actually see that these formulas are just actually equal. So how come uh, they are equal? So if you will try to uh, express the total moment here on the case of the bending in the case of the basic concept method, if you will try to express the total bending moment acting at the concrete element at service loads, which is again equal to the summation of the moment due to the dead load, live load, and the superimposed dead load. If you will try to express that as the sum of the balance moment here, which is due to the balance load here, and the unbalanced moment, which is again due to the unbalanced load here. And again, take note the sum of this are just equal to the total service loads. So if you will just try to express the total moment here on the formula for the basic concept method in terms of the balanced moment and the unbalanced moment, where in the balanced moment, we have found out a while ago that the balanced moment is just equal to the eccentric moment due to the eccentricity of the pre-stressing force, which is just equal to PE. So we can change MB here by PE. So if you can look on this equation, if you will try to look on this equation, uh, if you will express this in terms of MUB, therefore you just have to transpose PE to the left side of the equation and try to factor out C over I on these two terms. So the remaining term inside the quantity will just be the uh, negative, or I mean the M minus PE. So try to factor out C over I and C over I here together with the negative sign. If you will factor out them, you will have an expression equal to negative C over I times M minus PE. And since M minus PE is just equal to MUB, you can just replace M minus PE here by MUB. And the resulting equation will be equal to this, M negative C over I times MUB, which is again equal to M minus PE. So with that, we have seen that the formula for the basic concept method and the formula for the load balancing method are just actually equal, but just seen on a different perspective. Just like uh, what we have seen on the case of the C-line method. So the formula is different, but if you will try to investigate it, it is just equal to the formula for basic concept method, just seen on a different perspective. So again, they are just equal if you will try to compare. So technically, uh, you must have a similar answer if you will try to use the basic concept method and the load balancing method formula. Although in cases where the tendon profile or the profile of the pre-stressing reinforcement is varying with respect to the length, you have to take note that the force P that you will use on this formula or even on this formula must be the horizontal component of the pre-stressing force, just like what we did here. Because if you will try to imagine what is the direction of the pre-stressing force acting, say for example, at the end of this pre-stressing reinforcement, we know that the pre-stressing force is always tangent to the profile of the pre-stressing reinforcement. So if you will imagine what is the direction of the pre-stressing force acting at this end of the pre-stressing reinforcement, it is a inclined force. And since it is inclined, it has components horizontal and vertical. So that horizontal component, that magnitude of force must be the one that you have to use on these formulas, even on the other formulas that we have derived from the basic concept method and the C-line method. Although, for cases wherein the length of the simply supported beam is a very large length, you will encounter no problem on using the magnitude of the pre-stressing force itself instead of the horizontal component. Because for long span beams, the pre-stressing force is just approximately equal to the horizontal component of it for long span beams. But for the cases of short span beams, you can see that the horizontal component of the pre-stressing force is not anymore equal to the pre-stressing force itself. So in those cases, you have to use the horizontal component instead of the pre-stressing force itself. So again, take note of that. You have to take note of that for cases of having a profile with varying eccentricity. That is always the case for those type of concrete elements with tendon profile or pre-stressing reinforcement profile with varying eccentricity. Just you must always use the horizontal component of the pre-stressing force for the formulas for finding the total stress acting on the concrete element at every section, at any section. So that is how the formula for the load balancing method was derived.